Hi everyone, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're going to work through the brand new New York State Chemistry Regents exam, cluster by cluster. This is the second video in the June 2026 series where we're going to look at the chemistry of beverages cluster. If you're looking for a different cluster, check out the playlist linked in the description below, where you'll find step-by-step walkthroughs of the rest of the exam. Let's get started. As for all of the clusters, we're going to start by fully reading the passage, and then keeping in mind we'll probably have to go back to it. So for chemistry of beverages, soda is a carbonated beverage made by a process in which carbon dioxide, with a molar mass of 44.01 grams per mole, is pumped into the drink under high pressure to a concentration of approximately 8.0 grams of CO2 per liter of soda. The beverage container is then sealed to keep the solution carbonated. When the bottle or can is opened, the gas escapes and the beverage goes flat over time. Equation 1 represents this process. Consumers perceive soda as flat at concentrations less than 6.2 grams of CO2 per liter. 1 liter of the carbonated beverage was put into a bottle and stored in a refrigerator at 5 degrees Celsius. An identical bottle of the carbonated beverage was stored on a shelf at 25 degrees Celsius. Each bottle is opened and immediately returned to its original location. And then question 6 says, how many molecules of CO2 are still dissolved in a 1.0 liter bottle when the soda first is considered to be flat? Okay, so a bit of information there. So the first question, we want to know the molecules when it is first considered to be flat. So we kind of want like the maximum amount of carbon dioxide when it's flat. And the passage gives this to us because it says consumers perceive the beverage as flat at concentrations less than 6.2 grams of CO2 per liter. So all this question is asking us to do is convert 6.2 grams of CO2 to molecules of CO2. So we need to do dimensional analysis to solve this. Well, in order to do this, we do need to write a conversion factor. We need to know how many molecules of CO2 are in a mole of CO2. In order to do this, we can look at our reference table. And if we come to mathematical relationships on the back, we know that 1 mole is equal to 6.02 times 10 to the 23rd particles, right? That's Avogadro's number. So what we can say here is that 1 mole of CO2 equals 6.02 times 10 to the 23rd molecules of CO2. Looking at the problem, we realize that what we really need to do is get 6.2 grams of CO2 to molecules of CO2. So what you could do is you could convert this to grams to moles and then to molecules, or you could recognize that 1 mole of CO2 is also equal to 44.01 grams of CO2. And then we really have our conversion factor that we need. It's this. So I'm going to set this up like any dimensional analysis problem. I'm going to start with my 6.2 grams of CO2 on the top and put that over 1. Then we want to cancel out grams of CO2, and we want to get into molecules of CO2. And to do that, we just plug in our numbers. All right, as it's set up, the grams of CO2 are going to cancel, and we're going to be left with our desired unit, which is the molecules of CO2. When you do that, you should get choice 4, 8.5 times 10 to the 22nd molecules. All right, for question number 7, it says, identify evidence from equation 1 that supports the claim that the CO2 aqueous concentration in the bottle of the open soda on the shelf would drop below 6.2 grams per liter before the bottle in the refrigerator. Now, I will tell you all, as a chemistry teacher, my mind immediately went to the wrong place. I began thinking of relationships between solubility of gases in solution and solubilities of solids in solution, which could very well be used to explain this question, right? I could say that the higher the temperature, the less a gas is going to be soluble in solution. But that's not what this question is asking for. Specifically, this question is asking us to identify evidence from equation 1 that supports the claim that the CO2 concentration in the bottle of open soda would drop below the one in the refrigerator. Okay, what we need to know here is that the open soda is stored at 25 degrees Celsius and that the soda in the refrigerator is stored at 5 degrees Celsius. Right? This is a Le Chatelier's principle question. So if we look at this equation here, right, notice the CO2 aqueous, that's the dissolved CO2 in the soda, plus energy. When you put energy into that, it is going to form CO2 gas. Right? So our evidence from this equation is that energy is a reactant. If we increase the amount of energy, we're going to ultimately end up driving this reaction forward and forming more CO2 gas, which is what we don't want. We want it to stay in the aqueous form. So all I'm going to say is in equation 1, energy is a reactant. All right. Moving along. For question 8, it says that figure 1 shows that carbon dioxide gas exists in the headspace above the soda in the sealed container, as well as in the liquid. When a brand of carbonated beverage is bottled at 281 Kelvin and 191 kilopascals, 35 milliliters of CO2 occupies the headspace of a 355 milliliter bottle. For question 8, a student makes a claim that a 355 milliliter unopened bottle, stored on the shelf has less CO2 gas in the headspace than an unopened bottle stored in the refrigerator. Place a check mark in either the support or refute box below to indicate whether you support or refute the student's claim. Provide a justification using properties of solutions to explain your decision. So guys, if you remember what I said in the last question where my head went to the wrong place, now that thought has to be applied to this question, right? So what we should know is our solubility rules. We should know that as temperature increases, the solubility of a gas is going to decrease, right? So this could be my gas. Maybe you did a lab where you made a solubility curve that looked something like this. That was for a solid. Right, so this should be just one of those facts that you memorize. The more you heat a solid, the more it dissolves. The more you heat a gas, the more it comes out of the solution, or the less it dissolves. Right? This student is saying that the unopened bottle stored on the shelf, which we should remember from the passage is at 25 degrees Celsius, has less CO2 in the headspace than that stored in the refrigerator. That was at 5 degrees Celsius. Well, if it's stored on the shelf, that is at a higher temperature. So on the shelf, there's going to be more gas that comes out of the solution and thus more gas in the headspace. So for that reason, I'm going to refute the student's claim. I don't agree with that. And in order to justify that, I would say something along the lines of gases are less soluble at higher temperatures. You could mention that the bottle that's stored on the shelf is at a higher temperature. And then you could use that to justify that at a higher temperature, more gas will be out of the solution and thus in the headspace. All right, so moving along onto the next question. It says that some beverages stored in aluminum cans require a pH lining to prevent acidic drinks from corroding the metal. Figure 2 lists the pH of some common beverages. Figure 3 lists some acid-base indicators. So then question 9, it says how many of the beverages listed in figure 2 would require the can to have a plastic coating? Well, if we go back to the question, it says that the acidic beverages are the ones that need the plastic coating. Where does it say that? All right, so we need to essentially figure out what beverages are acidic, and then that's the number of beverages that require the coating. So a little review on acids and bases. If your pH is equal to 7, that means that you're neutral. If your pH is less than 7, that means that you're acidic. And if your pH is greater than 7, that means that you're basic. So we're looking for pHs that are less than 7. So that would be cola, that would be seltzer, that would be sport drink number 1, and that would be white grape juice. So that is a total of 4 beverages that would require the coating. Then question number 10, it says, which 2 indicators could be used to distinguish the 2 sport drinks from one another? So just for my purposes, I'm going to make a little table. So sports drink number 1, the pH is going to be 3.0 to 3.5. And for number 2, it's going to be just 8.8. So then let's just start evaluating indicators with respect to figure 3. So for choice number 1, thymol blue, if we look at thymol blue, well, under 1.1, it's going to be red, and then above 2.8, it's going to be yellow. So both of the beverages are above 2.8. So in other words, thymol blue would be yellow for both of them. So we can eliminate answer choice number 1. Answer choice number 2 also mentions thymol blue. Again, we'll eliminate that because both are above 2.8. They'll both be yellow. Moving along to number 3, brome crescel green. Brome crescel green, if it is below 4.0, it will be yellow. So for sports drink number 1, I'm going to add a little more to this table. Brome crescel green is going to be yellow because it's below the color change. And then if we notice here, above 5.6, that's when we're going to be blue. So 8.8 is above 5.6, so that one will be blue. So brome crescel green is definitely good. Then let's distinguish the other ones. So I'm going to look at phenol red. I'll add on to this table. So phenol red, below 6.8, it's going to be yellow. So number 1 would be yellow. And then above 8.0, it's going to be red. Well, sports drink number 2 is 8.8, so that would be red. So I'm really liking answer choice number 3. We'll just check indigo carmine for good measure. Indigo carmine, below 11.4, it's going to be blue. And if we look at both of these ranges, they're both below 11.4. So indigo carmine isn't going to tell us anything. It's choice 3. Hopefully doing state lab number 3 helped you with this one. So that's it for this cluster. If you found this helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can look at the next video in this series by clicking the playlist link in the description below. Happy studying.